Well, while we're on the topic of fluid statics, we need to take time to mention Pascal's principle. So first, let's do a quick review what we already know about fluid statics. One, there's a difference between absolute pressure, atmospheric pressure, and gauge pressure. So absolute pressure is found by adding atmospheric pressure to gauge pressure. So this symbol P0 stands for atmospheric pressure, and it's equivalent to either 14.7 pounds per square inch at the surface of the Earth, or 1.01 times 10 to the 5th pascals. Gauge pressure is the additional pressure that an object has by virtue of being at a depth within a fluid. And gauge pressure can be found by multiplying the density of the fluid times gravitational field strength times depth within a fluid. So all this is fine and good as long as objects are in a static situation at some depth within a fluid. But what about changes in pressure? What happens when we try to mechanically add pressure to a system? For example, we could use a syringe and attach a tube to the syringe, and perhaps that tube ultimately leads off to, I don't know, maybe something like a balloon. So a fluid is contained all through the system. What happens when we push on the syringe and increase the pressure immediately at this point just beyond the plunger of the syringe? A positive change in pressure appears at point X. But what about point Y, or point Z, or point P, or point Q, or any point? For this enclosed system, and that's the key to our study of Pascal's principle. It's a principle that applies to enclosed systems. How does this increase in pressure here compare to the increase in pressure at the other end? It turns out whatever the change in pressure is at one point is the change in pressure at all points. Changes in pressure are transmitted undiminished to all points within the enclosed system. Now that doesn't mean the pressure is equal at all points. Let's see. Let's draw some elevation lines. Okay, so before you ever push on the syringe, I would guess that the pressure at point B is greater than the pressure at point A because it sits at a greater depth and pressure varies with depth. And I would guess the pressure at point C is even higher still. But the question goes, when we apply a force here on the plunger of the syringe, how does the additional pressure at point X compare to the additional pressure at point A or B or C? And Pascal's principle tells us that added value of pressure becomes the same at every point. Okay. One demonstration of this comes from attaching two different syringes together. This is a fun classroom demonstration, in part because it seems to be counterintuitive. So it goes something along these lines. If I take a tube and connect two different syringes, and this fluid is totally contained in the tube and in the two syringes, then you present a challenge. You pick two students and you say you're going to have a hydraulic battle. You can either pick the big strong syringe or the small weak syringe, and you're going to put your thumbs or your hands on these syringes, and each of you push down with some force. The winner of this challenge is the one who can make their plunger fall as opposed to rise. Okay, so it's sort of the opposite of a tug of war. It's a push of war on these syringes, and who's able to effectively push their plunger downward. And so Your gut might tell you, well, the bigger one should be able to exert a stronger force. But if we take into account what Pascal's principle says, it says as one person pushes here and another one pushes here, the changes in pressure combined from the two volunteers' efforts has to be the same at every single point. So here's the thing about it. Pressure is equal to force divided by area. Or another way to think of this is force is equal to pressure multiplied by area. And the larger syringe has a larger area, so it would require a greater amount of force to be able to keep it from rising than the small one. So actually the person who pushes on the small syringe is the winner. She doesn't seem to believe it. A hydraulic lift works on this principle. So here's an oversimplified version of a hydraulic lift that might be used at an auto mechanic's shop in order to get underneath your car and do work on it. So the hydraulic lift is all based on Pascal's principle. If you apply a small force as seen by the small vector, you can actually amplify it and create a much greater force on the other side. And here's how it works. If the elevations are the same at these 2 points, then the pressure at point 1 and the pressure at point 2 before any effort is made to compress the fluid has to be equal. Pressure at point 1, pressure at point 2 should be equal to one another. And now this force, number 1, is applied in order to try to compress the fluid. And maybe it pushes down here and this much fluid gets displaced. Okay, well, there's an increase in pressure that shows up here. But that increase in pressure is transmitted to all these points x, and ultimately, all in an instant, that change in pressure shows up undiminished everywhere. And so the new pressure at point 1, P1 prime, is equal to P1 original plus delta P. So the same thing should be true here. The new pressure, P2 prime, is equal to the initial value of P2 plus the change in pressure. But we said that P1 and P2 had to be equal just due to the fact that they're at the same elevation, and Pascal's principle tells us the change in pressures have to be equal, so the final pressures on both sides have to be equal. Well, pressure is force divided by area. So the force applied on piston number 1 divided by the area of piston number 1 has to equal the force upward applied on piston number 2 divided by the area of piston number 2. So the force acting on the larger piston is equal to the small force applied on the smaller piston multiplied by a ratio, area number 2 over area number 1. And you can see the cross-sectional area number 2 is much greater than the cross-sectional area number 1. So this is a number that's much greater than 1, which means force number 2 is much greater than force number 1. To some people, that seems like you're getting something for nothing, but this doesn't violate the law of conservation in any way. In fact, to displace this much volume of fluid on the left side, the piston was pushed down a distance, we'll call it D. We'll call it D1 since it came from force number 1. Now over here, if the volume of fluid is the same, but the area is greater, then the amount of fluid displaced here is of much less height, D number 2. And remember, work and energy are both measured in joules, and work is force times distance. So in one case, you have a small force multiplied by a big distance, and over here you have a big force multiplied by a small distance. The amount of change in energy in both sides is the same. So there's really no violation. It multiplies force, but it doesn't multiply energy. This same principle is applied in the hydraulic braking system in most vehicles. More and more cars on the road are controlled, what they call drive-by-wire, but standard mechanical systems use hydraulic braking systems where a master cylinder sits not far from the brake pedal. So your foot pushes with the force F, and that compresses an enclosed fluid in a master cylinder. That fluid is a completely enclosed system, and in the end it terminates at some slave cylinders. Now, this picture actually has it all wrong. This is very misleading. It shows that the cross-sectional area of the master cylinder is large and the cross-sectional area of the slave cylinders is small. It should be the other way around. So this picture shows it in better detail. Your foot pushes, for example, with a force of 100 newtons against the brake pedal, and that causes a plunger to compress the fluid in the master cylinder that has a smaller area. It's a completely enclosed fluid, and the slave cylinders have a larger cross-sectional area, and so there's a multiplication of force. Now, depending on how much greater the area is, then the output force is that much greater than the input force. And it takes a large amount of contact force or normal force so that the friction force between the brake pads and the rotors is sufficient enough to slow your car down, right? Friction force is equal to coefficient of friction times normal force, and 100 pounds of normal force wouldn't be enough to do it, so we use a hydraulic system and take advantage of Pascal's principle. So in review, let's say it one more time. Pascal's principle can be stated this way, that the change in pressure when it's applied to, and here's the key, Pascal's principle is a principle that applies to enclosed fluids. That change in pressure is transmitted undiminished, meaning equal to all points within the enclosed fluid.